you have the mic?
Hello? Achoo!
So it's a pleasure to introduce Professor David Mond from Warwick University, and his short course is called On Singularity of Maps. Thank you very much.
Okay, well, it's a great pleasure to be here. It's the World Center for Singularity Theory, São Carlos. I'm sure that there's nowhere else where we would find such a large audience. And I hope the audience is still so large tomorrow. We'll have to find out. I'm going to write on the board, and as you all know, the audience has a method for controlling the speed of the lecture, right? Because the further away the audience is, then the bigger the lecturer has to write, and this makes the lecture go slower. So for tomorrow's lecture, you have to decide if you want the lecture to go faster or slower. If you want it to go faster, you sit further forward. If you want it to go slower, you go further back. Okay. Well, I didn't know where to start with these lectures. I didn't know what level to start. So I've written about 60, 70 pages of lecture notes. And today, I hope to cover the first 40. And of course, we're not going to cover all of these in any detail at all. And I hope that a lot of what is written in the first 40 pages is material that you already know. There's a lot of basic stuff like the Thom transversality theorem, the notion of a germ, the notion of the conical structure lemma, lots of things which are quite basic. If you don't know these, well then you can read the lecture notes. What I'm going to do today is focus on some examples, and I think if you hold on tight to the examples, then you can understand what's going on even if you don't have a lot of the basics. So what I want to do today is introduce some examples and do some calculations. And I've got some exercises that you can do yourselves, and that's the most important thing, that you learn to do the calculations yourselves. And I hope that you try to do between today and tomorrow, you try to do some of the calculations. That's what I would like to achieve. Okay, so I begin by talking about a different branch of mathematics, which maybe you're familiar with, and that is, I'm going to say a little bit about knot theory. A little bit about knot theory. So everybody knows that a knot is some curve. Let's make it do something like this. Okay, is that a knot? No, I still haven't got a very good picture there. No. Let's make it into a knot. I think that's a knot now. Yeah, okay. So this is a knot. Yeah, this is a trefoil knot. Now, how do you study trefoil knots? Well, you project them onto the plane, because knowledge is transmitted in books, and books are transmitted on two-dimensional objects called pages. So knots are studied by means of planar projections. But for any knot, there are many different planar projections. If you look at the knot, so you imagine looking at it from a certain point of view, and you see a two-dimensional image, right? This is what I've drawn, although of course I've indicated, using a convention, I've indicated overcrossings and undercrossings. But you've got to forget that. Just imagine a two-dimensional projection. And these pictures of knots are not unique. If I move the knot and look at it from a different position, I see a different picture. Now, the important point is that between any two pictures, you can draw a sequence of pictures, And this sequence is essentially an isotopy. Nothing changes, except for 3 types of move, which are called Reidemeister moves. So I show a picture. So between any 2 planar projections, isotopy plus a finite number of Reidemeister moves. So, what are the Reidemeister moves? Well, there's certain transformations where where the picture really changes. So let me show you, using this advanced blackboard technology. So here's the picture before. There are 3 different moves. 1, 2, 3. And in this picture, let's look at number 2. Look at number 2. We have 2 branches of curve which are close to one another but don't meet. Now, in the sequence of pictures, they meet and then they cross. And the same for each of these 3 pictures, we see a one parameter sequence. So here we see what forms this is called a cusp. Oops. And if we continue a little bit, we get this funny loop which appears. Now, again, this is something that you can experience. You can see this is a statement of physics. If you take a knot, this is what you see if you move it around. You see this picture if you look along the tangent line to the curve at some point. And from certain directions, you see this picture where you have 3 branches of curve crossing, apparently, in your image. And as you move your point of view, then you see a sequence of pictures like this. If you look here, this vertical is on the left of the intersection point of the other 2. Here it passes through, and here it's moved to the right. So, what is the basis for saying that these are the only transformations that happen in the course of changing from one plane picture to another? So the answer is that we have to look at the notion of codimension. So these are the codimension. So I'll explain singularities. I'll explain what this means. So every planar projection of a knot is a map from the circle to the plane. And I claim that these 3, the ones that you see in the middle, are the codimension 1 singularities. Now, I'm going to give you 2 definitions of codimension today. The first is a practical, an experimental definition of codimension. And this is very simple. For each of these pictures, we ask, what is the set of points in 3-dimensional space from which we can see such a picture? So in this example, I said, you can see this picture if you place your eye on the tangent line to the curve, and you look towards the curve along the tangent line. Because you're doing this, then the motion of the curve is directly towards you, and that means that in the planar projection, the tangent vector is killed, and you see a cusp. So this says that the set of points from which you can see this picture is formed by the union of the tangent lines to the curve. So for each point on the curve, you have a tangent line. Together, those tangent lines make a surface, which is called the tangent developable surface. And so I can see this picture somewhere if my eye is located at some point of the tangent developable surface. Okay, so that means that it's a codimension 1 singularity, because the codimension of the set of viewpoints is 1. So let me write this down. So codimension. This is the empirical definition. Later we do some calculations. Codimension of a singularity is the codimension of the set of points in 3 space from which we can see it, or see a singularity of this type. Okay, so this definition is only about this motivating example. I'm not talking about general singularity theory at all, and this is one of several stages in the lecture at which I say, well, this is optional. You have to try to understand because I'm trying to motivate, but I'm going to come back and go over this in a few moments in a more formal way. Now, I convinced myself, or I hope I convinced you, that this is codimension 1. By some other geometrical means, one can convince oneself that the set of viewpoints here and here is also a surface. And one can, in fact, make a list of singularities and discover that these are the only 3 types of singularity for which the set of viewpoints is a surface. For all other singularities, the set of viewpoints is of greater codimension. And now, from this it follows that the other singularities can be avoided. If I want to go from one view of a knot to another, so each view of the knot is associated with a point of projection, where I place my eye. If I want to relate 2 views, I travel from one to the other along a curve in 3 space, and this curve can be chosen so that it avoids all view sets of codimension greater than 1. So I'm only obliged to pass through the viewing sets of codimension 1. So that's how one arrives at such a list. Now, I've introduced the term codimension, and I've given a completely empirical definition. I want to start again in a moment with a formal definition. So maybe that's the moment to do this, but we're going to come back to this picture. We're going to return to this picture because there's something that has not been mentioned yet, but which is quite important for the purposes of this lecture. So, let me now begin the somewhat more formal definition. So first of all, definition. A map germ. So let me think. Perhaps it would be good actually to make a question. How many of you know the notion of a map germ? How many people know this definition? A germ of mapping. So, okay, so some people do, and how many people are prepared to say that they don't? So, should I believe this? So everybody knows the notion. I think Roberto, do you think that's a fair? I mean, yeah, okay. So I won't give this. Okay, so we study. Let's consider two germs. Suppose I have germs R n naught, R p naught, F, and the germ R n naught, R p naught, G. So these two germs are right-left equivalent. If there exist germs of diffeomorphisms as shown. So here I want to have a diffeomorphism here in the source and a diffeomorphism here such that phi G composed with phi equals psi composed with F. So that's a very simple definition. And we're going to study this notion. One uses also the term A equivalence for right-left equivalence. And this is the principal subject of this mini-course, the theory of right-left equivalence of map germs. And what I want to do today is introduce the notion of the right-left codimension, which is closely related to the empirical codimension that I defined a moment ago. So let me continue. Okay, now, a deformation of a map germ is a one-parameter family. So I'm just going to write it rather informally, F sub t, such that F naught is equal to the F that I start with. It is trivial, well, in fact, right-left trivial, if there exist germs, if there exist families of diffeomorphisms phi t and psi t, such that ft equals psi t composed with f composed with phi t. And now the codimension of f, or perhaps I should say the A codimension, and then this is the formal definition, is the dimension over R of the following quotient. So I take the set of all d by dt of f sub t, where t, when differentiated when t equals 0, and here ft is a deformation of f, and I divide by the quotient. I take the quotient where ft is a trivial deformation of f. So this quotient is thought of as a vector space, and I want to try to compute its dimension. That's the definition of codimension that I'm going to be using it's not at all obvious why it's related to the empirical codimension, which I defined a moment earlier, but we're going to forget about that for the moment and focus on this. So, let me take as an example well, wait a minute. Before we calculate any example, we ought to try to pin this down a little bit more. So notice that these two objects look rather, well, they're just sets. But of course, if we're to make any progress calculating any of the dimensions, we have to invest them with a lot more structure. So the first thing to notice is that the numerator, the top line, is equal to, well, the set of all germs of map Rn naught to Rp. So perhaps I should have emphasized that F is, I'm thinking of a map germ from Rn0 to Rp0, and I claim the numerator is the set of all these germs because, well, it's quite evident that if I take a family and differentiate, then the derivative, of course, is a map. So the inclusion here is obvious. The inclusion in the opposite sense is slightly less obvious, because if G is any germ from Rn0 to Rp, then Ft is F plus Tg is a deformation. And dft dt, when t equals naught, equals g. So every germ can appear as the derivative of a deformation. Okay? So this rather shapeless object here begins to take on a slightly more formal appearance as follows. So let's write the set of all germs. Okay, so here's the proof. But let me resume this sentence. The set of all germs of maps from Rn0 to Rp is just the direct sum of the set of all germs. So direct sum of p copies of En, where En itself is just the ring of all smooth germs Rn0 to R, okay? So, of course, as I speak, I realize that I left out things. At the very start, I should have said that I'm talking about smooth germs. Perhaps I should also ask you to ask questions. If you're confused by something that I have said or haven't said, it's probably a good idea to ask a question. It would certainly make it easier for me, and it might very well make it easier for the rest of the audience if you ask questions. So please don't feel that you have to wait until the end. I think questions can be very valuable. So, anyhow, we're trying to turn this rather vague and shapeless quotient into something a little bit more calculable. So the first step was to recognize that the top line, the numerator, is just a direct sum of p copies of a ring, the ring of all smooth germs. So this is not just a set, it's a vector space, and it's not just a vector space, it's a module over the ring En itself. What about the bottom line? So let's now look at the denominator here. So I better write up here. So the denominator, well, it's the set of all derivatives of trivial deformations. So that means it's the set of all d by dt of psi t composed with f composed with phi t. Well, let's not write any such stats, okay? Each of these is meant to be a family of diffeomorphisms. And now, if you actually use the chain rule, sorry, this should say when t is 0. So this is just a calculation by using the chain rule. This is just the following sum. df, the derivative of f, applied to d by dt of phi t, where t equals 0, plus d by dt of psi t at t equals 0, composed with f. Okay? Now, what we have here needs to be understood a little bit more geometrically. For each point, phi t, if I take a point in the domain, then phi sub t moves this point somewhere. And as t changes, I get a curve. And when I differentiate this and set t equal to 0, I get a tangent vector. So this d by dt of phi t is simply a vector field on Rn, 0. So this is a germ of vector field on Rn, 0. And this, by the same argument, is a germ of vector field on Rp, 0. Okay, so we've now seen what our numerator is and what our denominator is. Let's try to understand the algebraic structure a little bit more closely. Okay, so there's a basic diagram which is very useful to understand the structure of this quotient which I've just rubbed out. And this is as follows. We draw our map, Rn0, Rp0, and since it turns out that we're talking about vector fields here, we introduce the tangent bundle, Trn, Trp, each with its projection, and associated to f, we have the derivative df, which to each tangent vector in the domain gives us a tangent vector on the target. Now, the numerator in the quotient that I introduced before, so let's think about this. Suppose that I take d by dt of f sub t, and I differentiate when t is 0. How can I think of this object, this derivative? I want a way of thinking of it in terms of this picture. So, for each point in the domain, f sub t is a point in Rp. When I differentiate with respect to t, then what I get is a tangent vector. For each x here, f sub t of x is a curve here as t varies, and when I differentiate, I get a tangent vector. So, in fact, this is a map Rn naught to the tangent bundle, or a germ, over f. So that means that it goes up here, because for each point in the domain, f sub t is a curve in the target. When I differentiate, I get the tangent vector to the curve. When I set t equal to 0, this tangent vector is a vector at the point f of x. So it's a germ over f. And we need a piece of notation to describe the set of all these. I told you it's algebraic structure, but it's actually useful to give it a name. So the set of all these, or the is called theta of f. Theta f. And we've seen that theta f is just isomorphic to en to the power p. Okay, and isomorphic to en to the p. Okay, the direct sum of p copies. Now, here in the denominator, I have to obtain the set of all df applied to vector fields on the domain, and the set of all vector fields on the target composed with f. So let me continue some notation. Theta n is, by definition, the set of germs of vector fields on Rn0. Theta p, set of germs of vector fields on Rp0, and the procedure by which I obtain a trivial infinitesimal deformation here is that if I have a vector field on the domain, you should think of that as a section here. This is this vector field. For each point here gives me a vector. I compose with df, and that gives me a vector field over f. And this procedure, we have maps. There exist maps Tf from theta n to theta f, which send simply a vector field psi let's write it, Tf of psi equals df composed with psi. That's the procedure here. We take our vector field and we compose it with df. So if the vector field is thought of as a section of the tangent bundle, then by composing with df we get a map, a tangent vector field over f. And by the same token, we get a map from vector fields on the target to theta f. As described here, vector field on the target, I simply compose it with f. So if my vector field on the target is a section here, by composing with f, I obtain a vector field along f. So this is rather simpler, eta composed with f. And now, the quotient that we described before, we wrote down before, which was infinitesimal. Well, let's write this, just what I wrote before, d by dt of f sub t divided by d by dt of psi t composed with f composed with phi t, and I'm leaving out the such that's. This quotient can now be rewritten as theta f, so this is just our notation, over Tf of theta n plus omega f of theta b. And I remind you a little bit about the algebraic structure. So this is en to the power p divided by, now let's have a look at the denominator. So theta n, that's the set of germs of vector fields on Rn0, and it's fairly evident that that can be identified with n tuples of this module En. Each vector field has n components, each of which is a function on Rn0. So a vector field is specified by specifying n germs of function. So it's a member of En to the n, and a vector field in theta p is a member of Ep to the power p. So let's just look at this quotient again. So En to the power n sum omega f of Ep to the power p. So we have some kind of algebraic structure here, but it's a bit unsatisfactory because on the top line, evidently I have an En module, and here I have an En module, and indeed one can easily check that this map Tf from theta n to theta f is En linear. If I multiply a vector field by a function, then the result of applying Tf is also multiplied by the same function. So this is an En linear morphism, and therefore this is an En module. But this part of the denominator is not an En module because Ep has no structure as En module. Ep is an Ep module, or Ep to the power p is an Ep module, and not an En module. So this is one of the difficulties of the theory, that this object has a mixed algebraic structure. Or let's just say, I mean, I'm not using the word mixed in any formal sense. So parts are En modules, and parts are EP modules. In fact, the whole thing, the whole object, is an EP module via F. So perhaps it's confusing to harp on about module structure, but as a vector space, the top line and the bottom line are, of course, infinite dimensional. And if we want to do any computations at all, we need to have a lot of algebraic structure to enable us to carry out the computations. So the structure of module over these rings is what enables us to do anything at all, but, as I said, it's a little bit of a mess, because on the top we have an En structure, on the bottom we don't. What they do both have is the structure of EP module, because how to explain this? There's a ring homomorphism from EP to En, which one just usually denotes F upper star. F upper star of G is G composed with F. And using this, every En module becomes an EP module. You see, if I have a function here, I can take it over to En, and then if I have an En module structure, I can take this function, multiply the module and elements in the module by this composite. Okay, so I've written a lot of formal definitions, and none of this looks like one could calculate anything. So let's prove that that's not correct. Let's actually do some calculations. This is perhaps the most important part of what I'm doing. So calculations. So the first example, it will be the Reidemeister move of type 1. So if you remember, that was the map with this as its image. So in order to do any calculation, of course, I need to give you a formula for this. So let me to R20, f of t is t squared t cubed. So I'm not going to justify this, but let's just work with this example. You can certainly easily satisfy yourself that this parameterizes a cuspidal curve. But what I want to do now is to show you that the codimension is 1. Okay, so claim codim equals, so that the dimension of theta f over tf theta n plus omega f theta p here is exactly 1. So there is a big problem in the subject, and that is that the rings that we're looking at are not very well behaved. This ring En of C infinity germs is not even a Noetherian ring, and it would be preferable to work with the ring of, for example, germs of analytic functions. And that's essentially what we do. So let me just introduce a trick, or to be justified later. Calculate as though every germ was a formal power series. Well, a formal or convergent power series. So this is justified, but I'm not going to spend any time explaining why, but nevertheless, if we make this assumption, then we are able to calculate this in a quite straightforward way. So now let's have a look at the calculation. So first of all, let me think a little bit for a minute. Okay, so let's think about TF. In this case, from theta 1 to theta f. So vector fields on the domain just are functions. Remember, this is just E1 to the power 1. So this is a very simple object. This is E1 to the power 2. And what happens? I just take a vector field xi, and I map it to df of xi. Now, I'm going to use the following notation. I'm going to write elements here as column vectors, and elements here as single functions. So in fact, this, in this example, xi maps to 2t 3t squared times xi of t. So let's look and see what happens with the monomials which make up this object. So everything in here is a sum of monomials, and if we can find those monomials in the denominator, we can eliminate them from the quotient. So TF theta 1 is just equal to the E1 module generated by this 2t 3t squared. So in here, I find all multiples, because this can be any, I can take any coefficient at all multiples of 2t and 3t squared. In the same way, omega f of theta 2 is just the set of G1. So that just means the set of eta composed with f, where eta is has got these two components, eta 1, eta 2, theta 2. So that just means the set of all pairs, eta 1 of t squared t cubed, eta 2 of t squared t cubed, where eta 1 and eta 2 are in functions of two variables. But I want to pretend that we can do everything as though we were just talking about formal power series. So we're going to look at monomials. We're not going to worry about sums or convergence. We're just going to try to find which monomials we can get in this, in the denominator. So notice that that functions eta of t squared t cubed, well, allow all monomials or t squared, because t squared evidently t cubed. But now if I take, for example, the first variable and I square it, I get t to the fourth. If I take the product of the first and the second, I get t to the fifth. And if I take the second and square it, I get t to the sixth. And in fact, since I have now an unbroken sequence, I can multiply each of these by t squared, and t squared, t to the sixth, t cubed gives me t to the seventh, t to the eighth. I obtain all monomials from here on. Therefore, so that omega f theta 2 contains all terms of the form t to the p, t to the q, with p and q both greater than or equal to 2. Because I can obtain these by composing a function on the target with f. That's what I'm allowed to do using omega f. So what's missing in this quotient? Missing from quotient, theta f over tf theta n plus omega f theta p. In this case, I should have, of course, put here t to the 0, because if I take the constant function, then I just get a constant function. So the only monomials that are missing are t. t0 and 0t. But, as we saw, if I take psi equal to 1, tf of 1 is 2t, 3t squared, and so tf of 1 minus omega f of 0, 3y1. So if I'm taking coordinates y1, y2, coordinates on the target. So y1 composed with f is just t squared is 2t 0, and hence t0 belongs to the denominator. So we're able to conclude, allowing this pretense that everything can be done using monomials, that in the denominator we have every term except perhaps 0t. Well, is it possible that 0t is in the denominator? Evidently not, because the denominator is made up from these two parts. In here, we allow arbitrary functions of t squared and t cubed, so clearly t doesn't appear. In here, we allow arbitrary multiples of 2t, 3t squared, but we never see t in the second component. So, in fact, this possibly can be ruled out, and we can write the following conclusion. The quotient Tf of theta 1 omega f of theta 2 is equal to E1 minus T. So this notation means that if I think of the elements of these as being power series, then here in the denominator I'm allowed all power series except those involving the monomial T. Now, terminology. So, notation. This set is called the AE tangent space to F. And finally, we've seen that the codimension of F is the dimension, this is by definition, theta F over T AEF, and this is 1 in this example. So that's, to some extent, a justification for the assertion at the start that the codimension of this Reidemeister move was 1. So we've had to cheat, because I've given you a formal definition of codimension in place of the geometric empirical definition with which I started, but those two can be linked. And the other piece of cheating that we've had to do is we've had to pretend that we could calculate everything in terms of monomials. Well, that second piece of cheating again can be justified, and I don't want to spend time making that justification because I think it's more interesting to make the calculations and later come back to the justification if one wants to. I think that doing calculations is much more valuable at this stage than developing a general theory. So what I want to do is a few more calculations, and I would also like to show how to calculate these two examples. So let's have a look at those. And I'm not going to do these completely, but let's make a start. So if you look at this second picture, of course, we're not talking about a germ from R to R2 or from R0 to R2. This is a bigerm. So 2, or the Reidemeister 2, is a bigerm, and this is going to be written like this. We've got, it's made up of 2 pieces. The first one is parameterized in my, I'm going to use by parameter S, and the second by parameter T. So we simply send S to S squared, and the second to T minus T squared. Okay? Now, what's theta F? So what's theta F now? Well, if we consider arbitrary deformations of F, that means in particular arbitrary deformations of the first and arbitrary deformations of the second. So let me call this first one F1 and the second one F2. So this is theta of F1, direct sum theta of F2. And now I need to introduce notation. So in the last example, elements of theta F, where F was a germ from R to R2, were written as column vectors, 2 rows, 1 column. But now I've got 2 copies of this, so these are 2 by 2 matrices of the form. So let's see. A1 of S, A2 of S, B1 of T, B2 of T. So this represents an arbitrary deformation of the first function, F1, and an arbitrary deformation of the second, F2. So the 2 columns refer to F1 and F2. And I think the notation should be clear. What about theta 2? Well, we've got now germs of vector fields on the source, but the source consists of 2 points. So this is, if you like, theta 2. So this is E1 direct sum E1. So I'm sorry, theta, this is theta 1. This is the vector fields on the source. We've got vector fields at this source and vector fields at this source. And these are going to be written in the form alpha of S, beta of T. And vector fields theta 2 are as before. These both of these germs arrive at R2 at 0 in R2. So this is E2 direct sum E2. And these I write as column vectors, eta 1 of Y1, Y2, eta 2 of Y1, Y2. So I want to compute the codimension using this description. And I'm not going to complete the calculation because it will take a little bit of time, and because it's much better if you write this yourself. So let's just have a look. So TF goes from theta 1, and I want to use a piece of notation for the origin of coordinates here and the origin of coordinates here. So let's say theta 1, 0, prime, and theta 1, 0, double prime. So this is the theta prime is the origin of the s coordinate and theta t the origin of the t coordinate. So this maps to theta f, and if I take function alpha of s, beta of t, then this is mapped to tf1 of alpha, tf2 of beta. So that means in this, since here's f1 and here's f2, and remember that tf1 of alpha is going to be a column vector, and tf2 of beta is also a column vector. This is going to be alpha of s times 1, 2s times alpha of s, 1 minus 2t times beta of t. So we end up with alpha of s to s alpha of s and beta of t minus 2t beta of t. So we get a particular collection of 2 by 2 matrices, and omega f from theta 2 to theta f takes a vector field eta 1 of y1, y2, eta 2 of y1, y2, and maps it to eta 1 of s, s squared, eta 2 of s, s squared, eta 1 of t minus t squared, eta 2 of t minus t squared. So let's have a look and see what we get. So, for example, what's Tf of 1, 0? So I'm going to take alpha equals to 1, beta equal to 0. So I just get 1, 2s, 0, 0. Tf of 0, 1 is 0, 0, 1 minus 2t. Omega f of y1, 0 is going to be y1 composed with the first, so s, 0, t, 0, omega f of 0, y1, 0, 0, st, omega f of y2, 0 is s squared minus t squared, and omega f 0, y2, 0, 0, s squared minus t squared. We're just composing. And now, if you are prepared to continue with these very, very simple calculations and to pretend, as always, that everything is just a linear combination of monomials, then the conclusion of the exercise, so exercise show that the codimension equals 1, and indeed that the tangent space only needs one supplementary generator, namely 0, 1, 0, 0, is equal to theta f. So this is a calculation which you have to do for yourself. It's not much more than bookkeeping. You just have to keep track of the list of monomials that you're able to obtain and to see what it is that you can get and what you can't get by this procedure. So this is all described in the lecture notes. Let me leave to you show also that if we parameterize Reidemeister 3, which, if you remember, was this by, well, we need a trigerm now, STU. This is mapped S to, well, let's say S minus S, T, T, 0, U. This describes the three branches of the curve. Show also, actually this is not a very, probably not a very good parameterization. Let's use a different one. Let's use this, because then we can write something simpler. S0, 0, T, U, U. Then the codimension or the dimension theta f t a e f is once again 1. Okay, I want to do, so what have I got, 12, 15? 15 minutes, okay. Okay. So, now, let me go on and give a definition. So, an unfolding of f from Rn naught to Rp naught is a mapgerm f from Rn cross R d naught Rp cross R d naught of the form x u maps to f u of x u. So it's a parameterized, a level-preserving germ with f0 equal to f. So the only difference between an unfolding and a deformation is just that we retain the parameter. And now, two unfoldings f and g, both on the same parameter space, Rn cross Rd naught, Rp cross Rd naught, are equivalent if there exist germs of diffeomorphisms. So this definition is rather formal and long, but we have to go through it. So let's write it down, and you can digest it at your leisure. such that I want each of these to be of a particular form. I want each of them to retain the parameter. So phi of xu must look like phi sub u of x, u psi of y u is psi sub u of y u. So really we think of each of these as a parameterized series of diffeomorphisms. And I want to ask that phi sub 0 is the identity of Rn, and psi sub 0 is the identity of Rp. And then we ask such that f is equal to psi composed with g composed with phi. So in other words, they differ only by parametrized families of diffeomorphisms. If I have two unfoldings, they're equivalent if one can be transformed into the other by composition with suitable parametrized families of diffeomorphisms. And finally, an unfolding, let's say, G on a different parameter space, Rn cross Re naught to Rp cross Re naught is induced from f from Rn cross Rd naught to Rp cross Rd naught by a germ H from Re naught to Rd naught if G of xv is equal to f sub h of v of x v, where I'm using for f the notation as before, that f of xu is f sub u of x. So I'm writing, in place of u, I'm writing h of v, because I have a germ which takes v to u. And finally, finally we have a very important notion, an unfolding f is versal if every unfolding is equivalent. So, sorry, an unfolding f, I should be saying of little f, if every unfolding of little f is equivalent to one induced from big F by a suitable germ H. So this is one of the key notions, the notion of a versal unfolding. And we've gone through a certain amount of calculation with the purpose, eventually, of calculating versal unfoldings. So let me, without any more delay, state the most important theorem about this. So, theorem. An unfolding f of little f from Rn naught. Well, in fact, I want to allow multi-germs as well as monogerms, so Rns to Rp naught is versal if and only if the projections into theta f over T A E f of so I'm going to introduce some notation which I haven't defined yet. So here, what this means is that if I write f of xu as fu of xu, then by the fi dot, I mean d fu d u I with u equal to 0. So the derivatives of the deformation with respect to the parameters, now setting the parameters equal to 0, should span this vector space. That's the necessary and sufficient condition for versality. So this theorem was proved, I guess, by Martinet in the 70s, and we're going to state it I'm not going to go anywhere towards proving it, although in the lecture notes there is a suggestion as to how to prove the implication from left to right. It's quite easy to prove that if an unfolding is versal, then these projections span the quotient. What's much harder is the proof in the opposite direction. I will make no attempt to do that in these lectures because that's not what I'm interested in conveying. What I want to convey is just something about some of the examples. So, as an example of this, versal unfolding of Reidemeister 1 remember, Reidemeister 1 was T mapped to T squared T cubed. We saw that T AEF consisted of E1 minus T, and so all I need is to add a parameter times T. So naught T spans the quotient theta f over T AE f, and hence by taking f of T u equal to T squared T cubed plus ut, we get, versal deformation, versal unfolding. So that's example 1. Example 2, let's look for an unfolding So recall Reidemeister 2, S to S squared 0, 0, sorry, S squared, S squared T minus T squared, we saw that theta F over T A EF is actually spanned by 0, 1, 0, 0. Of course, this is not unique. There are many different choices of spanning vector. So, as versal deformation, we can take S, T. Well, we don't need to do anything to the second one, but to the first one, S squared plus U. So I've just added on a parameter, and the effect of this is to raise or lower the curve in the picture. So if this is Reidemeister 2, then when I add U, I simply raise the first of the two, leaving the second one fixed, and so we get the one parameter sequence that we saw. Okay. So, very approximately, and using a certain amount of cheating, we've calculated that these two have got codimension 1, and we've calculated a versal deformation of each of them. And now, in fact, if you draw pictures of the sequence of map germs that you obtained from these two examples, so here, t squared, t cubed plus ut, and the other was s squared plus u, then you get exactly the sequence of pictures here. So here, u greater than 0, u equal to 0, u less than 0. Here, u greater than 0, u equals 0, u less than 0. So if you want to progress in the subject, and if you want to follow the lecture course, you have to try to make sense of these calculations, and you have to calculate the third one. Okay? Now, there are lots of exercises in the lecture notes, and I'll indicate in a minute which ones it might be a good idea to read through and to do. But let me finish by making another remark. Each of these three has got codimension 1. But if we look at the three pictures, then on the right-hand side, in each case, we observe that in the image, the first homology has also got rank 1. So in each of these three pictures, there's a cycle, a one cycle, evident in this loop, in this pair of curves, and in this triangle. There's a one cycle which disappears when we return the parameter to 0. So I draw the one cycle, the vanishing one cycle in red. So one of the themes of the lectures is that it's not a coincidence that we have a vanishing one cycle. In fact, that the first homology has got rank 1 in each of these three examples. Now, on the left, we also have a vanishing cycle. Here, we don't have. The reason is because here we're doing real geometry. If we were doing complex geometry, which of course we can't see, then the vanishing cycle would be present in all three pictures, not just in this one. And so, in the rest of the lectures, I'm going to be thinking more about the complex situation, but always of trying to draw real pictures, and it's fortunate that one can actually draw real pictures with sufficient frequency that they do show what's going on over the complex numbers, at least in low codimension examples. So that motivates a certain amount of what we do. But what I want to do in the next lectures is to think about the homology of the image and to understand something of the relation between this homology and the codimension. And in each of the following 3 lectures, I hope to say something about open problems. In fact, that's not very difficult because there are quite a lot of them. What I'd like to suggest is that if you want to, you can leaf through the first sections of these lecture notes. So this will probably make you laugh, but look through up to page 40. Now, of course, we haven't covered anything like all of the material in the first 40 pages, but most probably a lot of the material is already familiar to you, but especially focus on the examples. So I would like to suggest that people should read So homework. Calculate. Okay. Yeah, that's it.
Questions? So before we thank the speaker again, well, the notes of Mond's mini course is available at our web page, of the conference web page. And but if you are not able to print it, or either if you want to have it printed, please just let me know, and I will make a copy for you. I will speak in Portuguese now for the students. As notas do professor Mond estão no site da conferência, no nosso site do encontro, do workshop. Se você quiser, se você não conseguir imprimir no laboratório, ou se você quiser mesmo a versão impressa, dê o seu nome para mim e eu vou providenciar, ok? So, thank you.